So hello, good day. So today we will be continuing on chapter 2, part 4, the fundamental of heat. So this will be the part 4, chapter number 2. Okay, so in this chapter we will be covering about heat and also the temperatures and also the heat transfer. Okay, so whenever heat is applied to a body, it receives a thermal energy. Okay, so we always have a misconception that temperature is heat. So temperature is actually the representation of the heat or the thermal energy. Okay. So the temperature rise of the body depends on the heat is received. So how much heat is received as energy. So the mass and also the nature of the material. So different material has a different capability of handling the heat energy. Sometimes it can store, sometimes it will immediately release. Each material has a different nature of towards or characteristic towards the heat transfer. Okay, so the relationship to calculate is Q. Q always representing the heat equals to mc, the changes in T. So M is the mass of the body, C is the specific heat capacity, so usually will be given okay for the material. So plastic is having a different specific heat capacity. So iron has a different heat capacity. So usually in the question it will be given, and changes in T is the changes in the temperature. So in Celsius, okay, and Q is the quantity of heat. So heat is energy, and it can be quantified. It can be calculated actually. Okay, so when it's added or removed from a body. Okay, so we see an example. So example one. So determine the heat required to raise the temperature of 200 liters of water from 10 degrees Celsius to 70 degrees Celsius, assuming the tank is perfectly insulated. So perfectly insulated means so there are no heat losses because of leakage. So it's perfectly insulated, meaning the heat only can go out from here or here. Okay, so all the informations are given. So the mass of water is 200 kilogram. So because yes, here they say 1 liter with 1 kg. Uh, so we know we have 200 liters inside. So it is actually 200 kg. So the mass of water is 200 kg. So it required is, so we apply back the formula Q equals to mc changes in T. So M is 200. Okay. C is given 4180, and changes in T is 70 minus 10. Okay, so we know the mass of water, the heat required is 50.2 megajoule. So megajoule mg. Okay, so there are three modes of heat transfer. So namely, we can, is conduction, convection, and also radiation. So all these three heat transfers has a different characteristic when we compare. So if a hot flame is placed near one end of the iron bar, so like here, so we have an iron bar. We are heating up one end, so this end. So we attach three thermometers. Uh, So the temperature rises to due to the increased vibration of each atom. So inside this material we have atoms, and atoms are arranging in an array. So when we are heating up, we are producing energy to the atom, and the atom will start to vibrate vigorously. So when it moves, vibrates vigorously, it will cause heat energy to happen. So we can see the one that closest to the burner it increase first, but as as the time goes, all the other thermometers also will start to increase in temperature because we know the heat is transferred physically by a process called conduction. So conduction, it always uses physical. So meaning the fire is applied directly to the metal, and the metal has a physical atom inside which started to vibrate and cause the temperature to rise. So this is what we call as a heat transfer by conduction. So conduction will transfer the heat physically by touch or contact. Okay, so based on the conduction process, the thermal power transmitted to the body can be calculated. So we can calculate using this formula. So P equals to lambda A T1 minus T2 over D. So lambda is the thermal conductivity, usually will be given. So A is the area, so if square, width times the length. If circle, you can use a pi r square. Okay. And T1 minus T2 is the difference in temperature between the opposite phases. So we have phase 1 and also at the back phase 2. So we want to find the differences in temperature in degrees Celsius, and D is the thickness of the body. Okay, we'll see one example for this. So the temperature difference between two sides of the sheet of mica is 50 degrees Celsius. So they already given. So this side is 120 degrees. This side is 70. So the differences is 120 minus 70. So 50. So if the area is 200 centimeters square, so centimeter square we supposed to convert to meter square. So it's already given here 0.02 meter square, and the thickness is 3.3 mm. So we need to convert to meter. Okay, and determine the heat flowing through the sheet in watts. Thermal conductivity is 0.36. Okay, so based on the information given, we can find the value of power, okay, thermal power. Okay, so P equals to lambda A T1 minus T2 over D. So lambda is 0.36, A is 0.02. Okay, and T1 minus T2 is 120 minus 70 over D is 3 mm, so 0.03 meters. So we get 121. Okay, so we have covered the first heat transfer by conduction. The second heat transfer is by convection. So what is convection? Okay, so convection is based on the movement of air. So it can be force or natural. So we will see later the differences. So the air plays a very important role in convection. So the air is in contact with the hot steel bar, warms up and becoming lighter and rise. The hot air moves upward. It is replaced by cooler air, which in turn warms up. A continual current of air is therefore set up around the bar, removing its heat by the process called natural convection. Okay, so this is a natural convection. So let's say the line is hot and heat up quickly because of sun. So what it will happen? So the air molecules here, it will be heated up and it will become light and goes up. When this place empty, the cool air will enter automatically due to pressure difference. Uh, then what it will happen once the hot molecules goes up, it will become cooled down and it will replace here and it will become a cycle. Okay, so this is what we call as a convection. Okay, so convection process can be accelerated by employing a fan or blower to create a rapid circulation of fresh air. Heat transfer by forced convection is used mostly in the electrical motors to obtain efficient cooling. Okay, so this is a active cooling, okay, which we usually use in the machines. So active cooling means we attach a fan. So the fan will suck up the cool air from the environment, and it will cool the parts inside the machine. And once the cool air enters, the hot air will automatically goes up. Okay, hot air goes out and it will become cool, and it will enter back. So this is the same principle of using a fan or aircon in the house. Okay, so this is active cooling. We attach a fan. So there can be a passive cooling also. It is a natural convection. So meaning cool air will enter through the inlet, and once the cool air enter, the hot air will naturally will goes up. So if by comparison, so this will be more faster in cooling compared to nature. Okay, so natural convection also takes place when a hot body is immersed in a liquid such as oil. The oil in contact with the body heat up, creating a convection current. So we can see an example here at a pot. So we are heating up the pot. So let's say you want to make a tea. So you put a water inside. How the water become cool based on this. So when we the fire is heating the bottom of the kettle, so the bottom of the kettle will become hot, and there will be a molecules attached to the bottom. So once it become hot, it will start to break, and it will become light and goes up. When it goes up, this place will be empty. The cool molecules will take place, and once this thing goes on, so at the end, all the molecule will be heated up, and the water will be hot for you to make your drinks. Okay, so this is a combination of force, and also we call it as a induced natural convection. Okay, so there can be losses due to convection process. We call it as a heat loss by natural convection. We can calculate it using P equals to 3A T1 minus T2, so to power of 1.25. So this is one process, one formula that we can use. So T1 is the surface temperature of the body, and T2 is the ambient temperature. So it's a bit different from the previous formulas. In the case of forced convection, such as the produced by the blower, the heat carried away is given by 1280 A times T2 minus T1. So T2 is temperature of outgoing warm air, and T1 is the temperature of incoming cool air. Okay, so we can have this to calculate. So see a few example. So example 3, a totally enclosed motor has an external surface area of 1.2 meters square. When it operates at full load, the surface temperature rises to 60 degrees Celsius in an ambient of 20 degrees Celsius. So determine the heat loss by natural convection. So we want to find the convection. So all the informations are given. So ambient air is 20. So the motor temperature is 60, and we have the heat losses based on convection. So how we want to calculate? So we use the first formula, P equals to 3A T1 minus T2 to power of 1.25. So 3 times weight 1.2. So 1.2 is given. So T1 minus T2 is 60 minus 20 to power of 1.25. So the heat loss by natural convection is 362 watt. So this is the formula for natural convection. So another example, a fan rated at 3.75 kilowatt blows 240 meter cube per minute of air through 750 kilowatt motors to carry away the heat. If the inlet temperature is 22 degrees Celsius and the outlet temperature is 31, estimate the loss in the motor. So we know this on the previous slide. So force convection using a blower, we use this formula. So like this case, so we know there's a fan for blow the hot air out. Okay, so P equals to 1280 times A. A is so A is 240. Sorry. Okay, so you can see A is the volume of the cooling air in meter cube per second. So here it is given 240 meter cube per minute. So what you need to do, so this 240, so in 1 minute you have 60 seconds, so you divide by 60. Okay, so T2 is 31 degrees Celsius minus 22 degree Celsius. So once you solve, you get the losses in the motor is 46 kilowatt. Okay, and the final part for this section is heat transfer by radiation. So we have covered conduction, heat transfer by conduction, heat transfer by convection, and this is the third one, heat transfer by radiation. So radiation, meaning there's some sort like convection, but this radiation is happening by natural without air. So earlier convection by the air movement. This is without air movement. It you still can get the heat transfer. So you can imagine you're having a fire camp. Okay, so you have a fire setup. Even though you are staying at a distance, you still can experience the hotness of the fire. It's because of radiation. Whether there's air or not, but you still can experience the heat. So this is the heat transfer by radiation. The similar concept happens when we have a sun radiating the heat maybe millions kilometers from our Earth, but due to the heat amount of heat that is radiated from the sun, even though we are staying millions of kilometers away, we still can experience the hotness of the sun. It's because of this radiation. So the heat of a body lost by radiation is given by P equals to Ka T1 to power 4 minus T2 to power 4. This is the heat loss by radiation. So T1 is absolute temperature of the body in Kelvin, and T2 is absolute temperature of the surrounding object by Kelvin. So meaning if the question give the values in Celsius, we need to convert it to Kelvin first before we use. And K is the radiation constant usually will be given. Okay, so these are the radiation constant which already calculated by the engineers. Okay, so for certain materials, so actually we have an extended list of this radiation constant, but for this example, I only take this. Okay, so we can see different materials have a different value of K or the radiation constant. Okay, so last example for today. So the motor has an external surface area of 1.2 meter square. Is coated with a non-metallic enamel. So we coating this motor with a non-metallic enamel. Okay, so the material is a non-metallic enamel. So determine the heat loss by radiation, knowing that all surrounding objects are at ambient temperature 20 degrees Celsius. So surrounding temperature is 20 degrees Celsius. So how we want to find? So first we find the value of T1 and T2. So T1 is the surface temperature. So surface temperature is given 60, surface of the motor. So 60, but we know here we need to calculate the temperature in Kelvin, not Celsius. So how to calculate? 60 degrees Celsius, or we add 273.15. So we add with 60. So this is the value in Kelvin. So whatever value in Celsius, you plus 273.15. So you get 333 Kelvin. So you round up. Okay, then T2 is the same. Surrounding temperature is 20 degrees Celsius. So 273.15 plus 20 equals to 293 Kelvin. Okay, so if we want to find the value of K. So we know the material is non-metallic enamel. We can find in this list. So paint or non-metallic enamel. So the value of K is 5 times 10 to the power of negative 8. We just reuse it. Okay, so K is 5 times 10 to the power of negative 8. So all the informations are known. We can calculate the power loss. The power loss by radiation is P equals to Ka T1 to the power of 4 minus T2 to the power of 4. So K is 5 times 10 to the power of negative 8. So A is 1.2 and T1 to the power of 4 is 333 to the power of 4 minus T2 is 293 Kelvin, 293 to the power of 4. So once you solve it, C is equals to 296 watt. Okay, so we have covered all the three types of heat transfer. So I hope it's beneficial for you. Okay, thank you.